we are going to be finishing off some vector functions today. And then we move on to 13.2, where we look at how do you integrate and differentiate space curves. And they're pretty cool. I'm using a different pen today. It's nice and skinny, but I don't know if it's showing up well. Is it showing up okay on your screen, or do you want me to go back to the other pens?
It's showing up.
It's fine. Okay. So we're going to look at some questions, essentially questions 12 and 13, which are, how do you find the point or points where a space curve intersects a plane? So that's kind of overlap. Let's get that one sorted out. And then we'll look at when does a space curve intersect, if it does, with another space curve. And that's pretty much all I want to do on this section. So I've got a 12 and a 13, so let me wind back and pick one of those guys. Let's do a version of, is that 12? Oh, let's do a version of 13 then. Right, in question 13, you have a space curve. It's a 3D one, and it looks like this. It's a sine t, it's a cosine t, and it's a t, which I happen to know is a helix. So if you wanted to draw it, it would go like that. And I know it's going up the z-axis because that's t, and I know it's a helix because of these two guys. That's a very common shape. Anyway, where does this helix meet up with this plane? And this guy here, if you put him onto one of the drawing softwares we get, he would look like this. Do you know the ones that look like an upturned cup? That's what that surface would look like. And can you imagine then that you've got a helix spiraling upwards, and it's probably going to meet that surface in at least one or two places. And our job is to find out where those places are. So if you think of that as being the x coordinate of the helix, which it is, that's the y coordinate, and that's the z coordinate of the space curve. And this is the relationship connecting x, y, and z together. If you fit these together, essentially it's all to do with substitution. So I'm going to replace the z with t, the x with sine t, so that's basically sine t squared, the y with cosine t, and we get that. Are you comfortable with the x, y, and the z being replaced by the x, y, and z of the space curve? So what you've now got is an equation in t, and it's such, oh, I picked an easy one. I didn't know it was going to be easy until I did this. Hopefully everybody here recognizes that sine squared plus cos squared is 1. So in this particular situation, there's only one solution, right? There's only one value of t. So can you imagine as this helix spirals up, it only cuts the surface once, right? It might cut it like it just touches it and then bounces inside. So the curve bit is getting bigger, but the helix is staying the same width all the way up as it spirals. So I need to find the coordinates. All I do is plug in 1 into the space curve, and it becomes the sine of 1, the cosine of 1, 1, which as a coordinate, because this is called a position vector, would be this point here. And that is it. I'm having a quick look at this question. Well, this is not question 12, actually. It's not even question 13. I took a bit of 12 and a bit of 13 and put them together. But it's still a good question, right? The process stays the same. And the next kind of question, the last kind of question, is all about a space curve meeting up with another space curve. So this is question 14, or at least like it. And I got my first space curve, we'll call it R1. And it's a t squared, and a t cubed. And I've got my second space curve called R2, and it's made up of A1 plus 6t, A1 plus 30t, and a 1 plus 126t. And we're trying to find out where this space curve and that space curve. Now, I could plug them in and have a look at it, but I'm going to just pretend I know what they are. Can you imagine that this might be what the first space curve looks like, right, in 3D, right? It's zigging, zagging, doing its thing. And then you got the other guy, R2, and maybe R2 looks like this. They might intersect, right? Right, they might cross over. But remember, this is 3D. Oops. So although visually it looks like they cross over, if you look sideways, you see they miss each other. So this might be an intersection point. This might be an intersection point. There might be no intersection points at all. Excuse me. The question says, find the points at which these paths intersect. If the answer does not exist, just type in DNE. So there might be 1 point, there might be 2 points. There might be none. Any ideas how we're going to find out? Based on the fact the only thing I know are the equations of the two space curves.
Set the x values equal to each other.
Okay, let's take the x's. And if you set them equal to each other, and you do a kind of rearranging, you get -1/5. Okay, that's possible. Anything else I should do?
Put that value into the other, like the y squared equaling the 1 plus 30, or yeah, the t squared. Yeah, and see if that works.
So, right, so plug in t here, -1/5 here, -1/5 here. If it matches, that's good. If that works, don't you then do it with the third one? If all three work, you've got a single point. Based on this, there can only be one solution, if there's any. We agree it has to be this number, because any other value of t won't the x's not match. Right, so let's see what we get. If we do it for the y coordinate, in R1, the y coordinate is -1/5 squared, which is +1/25. And if we plug it into y2, the y coordinate is essentially that guy. And what's that guy? That's -5. Okay, stop looking. Would you agree the y coordinates don't match? So the space curves, in fact, don't intersect. And what you might be looking at is the finger thing, right? Okay, they've got the same x. They might even have the same y, right? But they don't have the same z, right? So DNE. Just for argument's sake, because they randomize these questions, so maybe they'll randomize it in a way that it does work. If I use this and I plugged it in here and here, and the two y coordinates both came out to be 5, shouldn't I also have to treble check the z coordinates match as well? And if the z coordinates both are 49, boom, you've got your answer. If x's, the y's, and or the z's, right, whatever one it is, if one of them don't match, you are looking at a DNE, right? It does not exist. Now, in this particular question, when you match these up, there was only one t solution. But can you imagine in a different question where it was t squared and t? So you might get two choices, t equals 0 and then t equals 1. If that happened, wouldn't you have to try t equals 0 and see if they fit, and then t equals 1 and see if they fit? And you might get one that does and one that doesn't. You might get both work, or you might get none at all, because it looks like they're only giving you those choices. None at all, 1 or 2, right? So we're not going to look at situations where it could be more than 2 times. although I'm sure that could exist. Are we comfortable about the process? It's really substitution where everything gets replaced by t and then you solve. I'm going to move if we're good. So let's start our next section. Oops, Rory just turned up. Section 32, and we're going to look at differentiation. And tomorrow, I'm sure, integration. Space curves. The good news is, and we've already found out what the good news is, isn't differentiation and integration of space curves really just integration and differentiation like it always was? You just do it 3 times. So let's show you how that would work. In general then, if you had a space curve and it was, I don't know, f of t, comma g of t, comma h of t, then its derivative, called r dashed of t, not surprisingly, is f dashed of t, g dashed of t, h of t. So this is going to bring you back to Calc 1, right? You're going to differentiate things. They're all going to be using t typically, and that's not a big deal. Differentiation is differentiation no matter what variable letter is used. So let's give you some examples. So we're going to get some of the old cobwebs moving. You're going to have to differentiate various functions. Now, when you differentiate, there are rules for differentiation: power rule, product rule, quotient rule, chain rule. They're probably the ones you're going to use most of the time, right? Power rule, multiply by the power, reduce it by 1, right? Power rule. Quotient rule, that's when it's a fraction. Product rule is what you do when it is a multiplication of 2 functions. And chain rule is what you do when it's a function of a function. So if I wanted to differentiate this function, you'd get 3t squared plus 2. If I wanted to differentiate, remember we've got our differentiation. See, I've got my differentiation on today, right? When you differentiate, right, it's not the same as integration. This is a chain rule. So you go, the derivative of the t squared is e to the power of t squared times something. Isn't it times the derivative, in this case, t squared? So times 2t. That's where that 2t came from, right? It's the derivative of the t squared. Now, if you wanted to do something as ugly as that, there are 2 different routes you can go. Both will work. Since it's a fraction, couldn't I do a quotient rule if I decided to go that route? And this would be called f, and this would be called g. And the quotient rule has a formula, f dash g, take away f of g dashed over g squared, and that would work. An alternate method, I don't care which one you choose, is to realize that you can write this guy as t squared plus 1 to the power of negative 1. And if I write it that way, instead of using a quotient rule, we will use the chain rule. Okay, which one of those 2 methods do you want me to do? I mean, which one do you just want reminded of? I don't know, whatever. Which one would you like me to do?
We do chain rule.
Chain rule is, okay. So if you write it like this, then multiply by the power and reduce the power by 1. finishing with the derivative of whatever is inside the bracket. So in this case, the derivative of t squared plus 1 gets you 2t. Now what I'm going to do is I'm going to make that, and this guy is going to come downstairs because of style points. So the answer ends up being negative 2t on the top and a t squared plus 1 squared on the bottom. And we now have our derivative. Are we okay with that method? Now, not every fraction is a quotient rule. If the fraction is a number on the top over something, you can certainly turn it into a chain rule question, right? But if there's terms on the top that have t's on it and terms on the bottom that have t's on it, you really have to do the quotient rule, right? There's no way of avoiding it. And some people just like using the quotient rule for all of those questions. You know, if they see a fraction, they just do quotient rule, and that works. Me personally, if I was doing this as working, I would do the kind of the messy bit. It's like scratch paper and just put the answer in once I've got it. Because, you know, you don't really want to have to write down 3 or 4 lines of working, because then you have to repeat all this over and over and over again, right? Seems a bit pointless. We're happy with that first one? Right, let's give you some more space curves that we're going to find derivatives of. Let me see if I can use the homework. That gives me ideas. There we go. So this one is a bit like question 1. Okay, what method shall I use? Don't need to get the answer yet. But what method should I use to differentiate e to the power of t cubed?
Chain rule.
Yep. And you get e to the power of t cubed times the derivative of t cubed. So that's where that 3t squared was coming from. Surprisingly, the mistakes that people make aren't always on the hard ones. Sometimes it's the easy ones that catch you, because you forget what hat you're wearing. What's the derivative of negative 1?
0.
Yeah. Do you know if you were wearing the wrong hat, couldn't you put minus t down by mistake? Because you forget that you're differentiating, right? You know, sometimes. Trig does that a lot. Don't people in trig very often integrate when they mean differentiate, or vice versa? So watch the sines and the cosines, because they're very common mistakes. Oh, that's a challenge. What is the derivative of a natural log? In this case, the natural log of 1 plus 6t.
6 over 1 plus 6t.
Oh, you nailed it. Technically speaking, this is a chain rule. The derivative of a natural log is 1 over the thing. So it's 1 over 1 plus 6t times the derivative of 1 plus 6t. That's where the 6 on the top came from. Let's play about with some more. Oh, good one. Didn't take far. I guess there's just so many things that you have to differentiate that there's lots of choices. You know, lots of examples. I just looked at this one and I immediately saw it and I thought, oh yeah, this is going to get people. No, I want to get you, but it does get you thinking. Tan 7t is a chain rule, but we need to know what the derivative of a tan function is. So what's the derivative of a tan?
Secant squared.
Good. So in this case, it's the secant squared of 7t times the derivative of 7t. That's what makes it a chain rule. So you get an extra 7. Oh, this one will really challenge your memory. What's the derivative of a secant?
Tangent secant.
Okay, I call it secant tan, but tangent secant is correct. So secant tan. But technically, isn't it a chain rule? So you differentiate by the, well, sorry, you multiply by the derivative of 4t, right? And that's where that extra 4 at the front is coming from. What about 1 over t to the 4? The simple ones can throw you. Is there a better way to write it that might make finding its derivative easier?
You can write it as t to the -4.
Right, if you write it like that, would you agree it's just a power rule? Right, multiply by the power and reduce it by 1. So what would that give me? -4 t to the -5, -4 over t to the 5, right? For style point reasons. Now, when you did Calc 1, off the top of my head, you probably did at least 4 weeks of differentiating different things. Yet in this class, you're expected to know all those different differentiation situations. Right? Like now, like not all will give you 4 weeks to catch up, like right now. Next one's boring. Next one's pretty obvious. I'm scanning through them. Next one's powers, so we don't need that. No, okay. That, I'm sure there's more. I'll do one of my own. Because there are a couple of situations I didn't see, and I want to do them. So, t squared e to the t, that's the first one. T plus 1 over t squared plus 1 is the second one. And what shall I do for the last one? E to the sine of t squared. And the reason I chose those 3 guys is that I think we need to see some of the rules that we haven't really touched on. What method will you use for t squared e to the t?
Product rule.
Great. What about the middle expression, that fraction? What rule would we use for that one? Quotient rule? Yeah. So lips moving with a Q kind of look. What on earth are you going to do with this last guy?
Double
Chain
chain rule.
Yeah, it's a chain rule of a chain rule. Right. I don't think we saw that today. So I'm going to take each one of these guys and kind of do them over here as working. And then once I've got the answer, we'll just stick the answers in, right? That seems to be the best, most economic way of doing it. So here is our first guy. Now, that's going to be called F, and this guy's going to be called G. And the product rule is F dash G plus F of G dashed. So differentiate this guy, you get 2t, leave that guy alone. Plus, leave that guy alone and differentiate e to the t, which is still e to the t. And then if you want to be, as I would, style points, pull out a whole load of common factors. So what would I get? I'd get t, e to the t, 2 plus t. Now the second one is t plus 1 over t squared plus 1. In this world, the top is called F, the bottom is called G. And if you want to do the quotient rule, it's F dash G, take away F of G dashed, all over G squared. The derivative of the top is 1, leave the bottom alone, take away, leave the top alone, and differentiate the bottom. And then the whole thing on the bottom gets squared. If you distribute this, you get t squared plus 1, take away 2t squared, take away 2t. And you get 1 minus 2t minus 2t squared, which I'm pretty sure can't be factored, so that's as good as that's going to be. And the last one. Right, it's a chain rule inside a chain rule, Russian doll question, really. E to the power of this guy is e to the power of this guy, followed by the derivative of sine t squared. Well, if you differentiate the sine of t squared, you will get the cosine of t squared times the derivative of t squared. And the usual convention is simple to worse case. So 2t cosine of t squared e to the power of the sine t squared. Okay, worst case scenario, right? The ugliest derivatives, but you know that belongs to the questions. Are we comfortable that if I give you a space curve, you know what to do to find its first derivative? Right. If you can remember your Calc 1 stuff, you'll be fine. Okay, let's move on now. The next thing is how to find what is called the unit tangent vector. Okay, the unit tangent vector is very often called capital T of little t. So if you see a find capital T, right, because they have the ability in textbooks to be able to get away with this. So you might just be asked to find T, right? I've made it as bold as I can think it, right? So how do you find the unit tangent vector? I said it's a formula, and it is. It's the derivative vector divided by the magnitude. So basically, you just find the derivative, right? In space curves isn't the derivative of vector, right? So you find the derivative vector. And then you find its length and divide by that length, and won't that make it a unit vector? So a unit tangent vector is essentially just a unit vector in the same direction as the first derivative, right? So you can imagine if you did it, that pen was the derivative at a point, couldn't you have a vector that's 1 unit long? And this would be your unit tangent, and this would be your r dashed of t. Parallel, right, pointing in the same direction. I'm 1 unit long, you're whatever it is. So let's show you what that might look like. You're going to be given a space curve, typically. Let's keep the space curve simple. And we're being asked to find the unit tangent vector at a specific point at t equals 2, right? So your question would be to find the unit tangent vector at a specific place on the curve. Well, you find the derivative vector. Power rule, power rule, power rule. You then find the derivative vector at 2. 2 lots of 2 is 4, 3 4 is 12, 1 more makes 13, 5. And the unit tangent vector at 2. Well, shouldn't I find the magnitude of this vector? Oh, I did the double brackets by mistake, but that's also a vector. So what's that going to be? 16, 169, 25. And that's going to be, let's see, 16, 169, 25, 210. So it's going to be the square root of 210. So the unit tangent vector is this guy, 4, 13, 5. So you're probably going to write it like that. If you're really lucky, WebAssign might say that's fine. It might need this. If it's going to be really, really pernickety, and then you'd have to cancel it down a little bit. I'm trying to think of every possible combination in the world. And I'm making the assumption that the square root of 210 can't be simplified. So can you see that you might just have to, you could end up spending more time trying to make it look pretty than you actually did getting the answer, right? Because square roots, unless they're really nice and give you the square root of 25 and the answer is 5, you're going to have to play about with making it either that version, or probably worst case scenario, that version. Just so WebAssign is happy. Are we good about how to find a unit tangent vector at one given point? Do one more than just to be sure. I'll pick one of theirs. This one is like question 6. Space curve is cosine t, 5t, for sine of t. And we're being asked to find the unit tangent vector at t equals 0. Okay. The derivative. Just to check, what's the derivative of cosine t?
Negative sine t.
Correct. You had your right hat on. Were some of you thinking positive sine t? Because you had your integration hat on, if you did. Now, at 0 is going to be negative the sine of 0. That's fixed. It's 5 all the time. And 4 cosines of 0. Well, that's 0. This is 5. And this is 4. And now I'll find the magnitude of this vector. And it's going to be 0 squared, 5 squared, 4 squared, 25, 35, 41. Can't think of anything to do with 41, so it looks good. The unit tangent vector at 0 then is this fella. And I'm just going to put dot, 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 dot. You know that there's different ways of writing that to get WebAssign happy. Yeah. Stick it inside, rationalize the denominator, simplify it, whatever it takes. At least you can't do anything to square root of 41. It's not like the square root of 8 that could turn into 2 root 2. At least you don't have that issue. It'd be really nice if WebAssign. Has anybody done this yet? Is WebAssign happy with this kind of answer? Or do you have to bring the square roots inside? Has anybody experienced that yet?
It's okay with it. When you put the square root at the bottom. But I had some questions that would be a little finicky with it.
So if I pick you right, is that what you mean by putting it at the bottom?
Yeah.
Right. So did you try that to see if it liked that?
I had some questions that liked it and other questions they didn't.
Oh God, that's the most annoying answer. It's not your fault. That's the horrible answer, because what that says is sometimes it'll work, yeah, and then sometimes it won't work. So I guess you'll find out. You know,
I think most of the
eventually.
time when it does work, when it doesn't work, they were like looking for saying that this could be simplified down.
Oh, so there's some other reasoning behind why it could be better. Right. Okay. So there might be a logic behind why one version's good and the other is not so good. I feel good about it, but I'm not. It's not me that's got to feel good. It's you lot have got to feel good. Do you feel happy about finding the unit tangent vector at t equals 2, at t equals 0, at t equals 20, whatever number they are? Do you feel comfortable with that type of question?
Yes.
Okay, then I shall move on. If you feel comfortable, I feel comfortable. Right. So the next bunch of questions, essentially 8 and 9, but I'll do a scroll in case it's 10. No, just 8 and 9. They are asking us to find all sorts of things. I can't think of anything else to say. Using derivatives. So let's just pick my own example, and I want to keep it, again, keeping it simple so that we can just focus on what they might ask you. So you'll be given a space curve, and then they will ask you to find various things. They'll ask you, for instance, to find that guy. In this case, that's just power rule to e to the t. And then they might ask you to find this guy. I don't think we've mentioned second derivatives yet, because I can't recall doing it. But I don't think it should be that hard a concept. How do you think I'm going to find the second derivative? R double dashed of t.
Take a derivative.
And it kind of intuitively doesn't that kind of make sense? If you were the first person that had to figure it out, wouldn't that probably be the way you would figure it out? Yeah, you probably just differentiate everything, and you do. It worked perfectly fine. So in this case, what, 6t0 and e to the t? That's good. Then you might be asked, in fact, I'm looking at a question where they do exactly that. Where you're asked to find that guy. Now, remember cross product? Now, normally when you did cross products, weren't the two vectors 1, 2, 3, 7, 8, 9, right? There were numbers in, right? But that doesn't mean you can't get a cross product when the vectors don't all have numbers, right? When the vectors are functions of t in this case. So I'll set it up the exact same way that we would. When you go I, j, k. The first one is him. So you go 3t squared 2 e to the t. The second one is him. So you go 6t0 e to the t. Are you comfortable about the cross product setup, how you would set it up in this particular world? So far, so good? Now, so many i's, take away so many j's, plus so many k's, right? That's how you set it up, I, j's, and k's. Remember the middle ones to subtract. And the rules are not going to change. I want I, so I'll cover up those two guys. Major diagonal, 2e to the t, take away nothing. 2e to the t is. If you cover up the middle one, it's a bit messier there, but won't it be major diagonal, take away minor diagonal? Right, these two is the major, these two are your minor. So what do I get? I get 3t squared e to the t, subtract 6t e to the t. And then the k version, major diagonal nothing, take away 12t, 0 take away 12t is negative 12t. And then make it look pretty. 2e to the t, comma. Yeah, not really a lot happened here. Negative 3t squared e to the t plus 6t e to the t. And this guy here is what, just negative 12t. Didn't say the answer was pretty, but isn't that the cross product of the first and the second derivative? Now, you might think, why would you want to do that? Apart from just the fun of algebra, right, where you get you to do stuff. This fella here is related to a thing called the curvature. It's a property of space curves. And curvature is essentially a number that tells you how curved a curve is. And you think, what the heck is that? Can you imagine that I have a space curve that looks like that? And then I have a space curve that looks like this. And then I have a third space curve that looks like this. They're all curved, agreed? But they're curved differently in how quickly they change direction, for want of a better word, right? Would you agree that this one takes its jolly old time to curve? So he might have a curvature, and the letter they use is called kappa, and he might have a curvature of 5. Now, this circle is very curved. Would you agree that it changes direction quite quickly, at least compared to that, right? So this might have a curvature of 10. And this helix, well, can you imagine, I know it's meant to be 3D, but can you imagine a helix? It's faster than that, but not as fast as this. So this fella here, he might have a curvature, you know, like 7. And so this cross product will tell you the curvature, right, a property called the curvature of a space curve at any given value of t. And the reason why that's the case is that for some functions, the curvature is the same all the time, like a circle. But for other functions, can you imagine that at this point here, it's changing direction quite quickly, whereas up here, you know, it's taking its time. So that any given value of t, the curvature could change, right? So how quickly it's changing direction may be different. For instance, for circles, the curvature is always the same number, because any given point on a circle, isn't it changing direction the same amount? And just because I want to, what do you think the curvature number is for a straight line?
Could it be 0?
Yes. Would you agree a straight line is the least curved thing in the universe? You couldn't get anything less curved than a straight line. Now, the other one, well done if you can guess this. What thing would have a curvature of infinity?
Is it a point?
Well done. Yes. A single point in 3D space has infinite curvature. I like a straight line being 0. In my brain, that makes sense, right? A straight line ain't got any curvature, so kappa should be 0, right? Here we go. If you take a circle and you make it turn quicker, the kappa might move up to 100. And if you keep shrinking that circle, won't the kappa become 1,000,000, 1,000,000,000,000, 1,000,000,000, right? If you can just keep doing it, won't a circle turn into a point in space? And that point in space would have infinite curvature.